I learned this from you.
I hate setting up Zoom now. I had to do this for Dr. Zha's class,
Yeah.
and I forgot to record audio,
Oh.
and it was like their presentations. It was like
Oh no. Was he mad?
He was tight, but then he was like, "Okay, just tell me like, what do you think that they deserve?" I was like, "All right." And so yeah, the lighting thing was also tough because like the way that the projector was shining the light, it oversaturated the whole thing. So you couldn't see anything on the actual projector. It was just white. You know what I'm saying?
Mm.
Must be a hard class, man. There's only two people.
Hey, morning. On lights on. I think that covers everything. Ooh. Okay. Hey, morning. Um, okay. Step outside. Quick second. Let's wait this here.
Yes, sir. Homework that? No, I was, considered back then. Homework? Yeah, I was here. And it has given more than 10 days, so I think it's gonna take more time. Yeah, I was just taking a look at it, but I couldn't get his code to run all the way. I was just curious if anyone else is running it. I guess so, it has to be defeated. Yeah, well, I think he did like. Yeah, he did the base automation thing, so I think it will be something similar. Yeah, he already uploaded that code, if you might be able to. Yeah, but he has like, the first part of the code is just like, you just like, clone the repo, and then he has a part of it that already is supposed to be working with like some kind of, facial, like. It looks like a mask over your face, but it doesn't run all the way. So maybe I think like they might have adopted your because I know are you running the same environment as the first homework? What's that? Are you running the same environment as the yeah, I still have the part. You had a number? Yeah, it was. Anybody talk to you about the first part of the homework? It's like, when I try and run on the mask, they like it. So, we're used to like, so. Like, you like, outline the mask.
Yeah,
I did, Microsoft or whatever.
yeah.
Kind of gets an error.
Oh. Well, what's it say?
I can pull it up. Some. Right, I don't know if I think I set up the environment. Stuff.
I mean, I made it from scratch, so it's not impossible that it has issues. I tried to make it as reproducible as I could, but
Yeah, I was just.
could you come up front? We're gonna do a quiz today, so I wanted to post on Piazza asking everyone to sit up front, but I forgot. Ooh, okay. I think I get what the issue might be.
Is it because
but
I'm running it in?
I think so, yeah.
Oh, okay. I think it's, oh.
I don't remember either.
Oh, it's- Oh, word.
I think first step was, yeah, overlay. Window, okay, window popped up, so
Yeah, so this is where usually, or at least when I was doing it yesterday, I would do this, and then so I hit done, right?
yeah.
But then it gives me that.
Could you go to overlay filter,
Yes.
line 17? Let's see what's there.
Not sure where it's. I'm gonna say where it is. This is great.
Line 17, okay, segment overlay object is returning none. Where's the function defined? Segment overlay, could you open segmentation.py?
Mhm.
And, okay, scroll down a little bit. Let's see what the, further.
Or
Keep
where you
going,
want,
keep
which one do you
going.
want, run over there?
Yeah, that function at the end, segment overlay object. Okay, starting segmentation. Do we see all of those prints? Image loaded. Okay, rectangle selector, applying graph to it. Was that print in here? Okay, it is. And then. Okay, yeah. So that's the first part to implement.
Oh, okay, I see. So
Yeah.
this is where we're supposed to start implementing?
Yeah.
Oh,
yeah.
okay, so sorry. That's
My bad. I didn't remember off the top of my head
No, you're good.
how I
I should
structured
have
it. but-
read more into it. I thought that this part was just already like an example kind of thing, so
Oh,
that's my mistake.
yeah, no, you're fine. I didn't remember either, and I made the thing.
Yeah, I think I just kind of got to it and I was like, oh, it's just, so, sorry about that.
People just walking in. We're doing a quiz today, so I want everyone up front, kind of like an exam, leave one seat. If there's spaces up front that you would be able to sit in, leaving one seat, and I see one of those empty and someone out back, then everyone gets 20% taken off their exam, off the quiz. So I know positive reinforcement usually works better, but um, that will depend on the rest of the class and the choices they make, I guess. I mean, it's going to be towards the end of the class, so I'm probably going to have to ask people to do it again. But people aren't going to fill up space up to there, I'm sure. So if you could come front. There's a quiz today, so come on up front, leave one seat. Wise choice. That's still like middle of the class. That's not front. So everyone, I want everyone up front as far forward as you can. Oh, it's 10:35. Okay. Okay. I'm going to start in just a second, but for people who just walked in, we have a quiz today, so I want everyone up front. If everyone's not at front when we start the quiz, then I take 20% off everyone's quiz points. Um, with that, let's build on some of the stuff that we talked about. That's still way too far back. Could you come up front, please? Today, we're going to talk about diffusion models. Last class, we harped about GANs and said they were awesome. We saw a bunch of really cool examples of what they can do. I drew a sort of anatomically impossible cat, and it was still able to generate a cat that sort of conformed to that structure. So today we'll look at cases where they don't do so great and why that is and how we can do better. We sort of touched on it when we went over the diffusion process last class, but GANs, what they're good at is you give them a distribution of things that have some sort of overarching structure or pattern to it. Like faces generally look like faces, right? So giving it a bunch of faces, you can ask it to sort of generate something that would fit the distribution of all faces. That works because it's got this sort of implicit constraint to what a valid prediction would look like. So for aligned faces, it works pretty well. But when we use unstructured images that aren't sort of consistent across the entire distribution like faces are, it starts to fall apart. This looks like something out of a nightmare, honestly. With all of the stuff that it's hallucinating in the dining room. This is supposed to be a dog, but I'd be terrified if I saw that. So to improve our ability to generate images, we need to come up with a different formulation for the problem. And we need a foundation to talk about that. So noise is something that we talked about early on in the class as part of the acquisition process. You get noise either from things interfering with your sensor or what sort of lighting conditions you have. The particular kind of noise that we care about is just uniform random noise. So if you have a really clear image and you add randomness to it uniformly across the entire image, then that's sort of what it looks like. And during acquisition, this happens due to things like just low light and your sensor in the camera is just trying to guess what is there beyond what it can see, or a high ISO, which has to do with how sensitive the sensor is to light. We can take that idea and think about what we can do with that. So if you have a clean image and you add some noise to it, then you have both a noisy and a clean image. You can use the noisy image as your input and use some autoencoder style network that also predicts images directly to guess what the clean image must have looked like. So it's implicitly learning a model of noise and how to separate that from an image. So clean image, add noise, and do the reverse. We're solving the reverse process, and we have an easy forward process that we're able to apply to build our data set. Epsilon is just a term we use to sort of represent the noise that was added to the image, so that we can quantify that and use that information as part of our modeling process. We can extend this process to do it a whole bunch of times. So we have some function that gives us noise, which we add to our image. We do that a whole bunch of times. And then eventually, just logically, when you keep adding noise to an image, you're going to end up with nothing but noise, because all the original content will eventually get overpowered by the amount of noise that you've added to it. And we can apply the same idea, which is if we're able to go from just one step of noisy to clean, then we can go from 2 steps of noisy to 1 step noisy and extend that idea, pushing it to its logical conclusion, which is that from complete noise, you're able to sort of guess what image could be in there. We can use that to build a formulation, which is the core idea of diffusion models. And we call them diffusion models commonly, but the paper that introduced this premise was called, the model in that was called the denoising diffusion probabilistic model. Breaking down that name a little bit, what we're estimating, it's probabilistic in nature since you're trying to estimate priors, if you think of it in Bayesian terms, where this is what you would have started from to end up at this. So we're trying to guess the inverse of that. What we can have our model predict instead of predicting the image directly is we predict the noise that was added to the image rather than a less noisy version of the image. So once we have that noise, we can subtract it from a noisy image and see how close to what it should have been, how close it was to what the input was. So that subtraction is something that's an additional step that we do before computing our loss. If you think about what GANs do, they're kind of like that process where the generator part takes in some random vector input and generates some synthetic image that would that is designed to confuse the discriminator. In a diffusion model, what's different is that we're doing this iteratively, and we take an input image, add noise to it. Our output image has less noise rather than being completely denoised. So since we're breaking the problem down into several noise levels, that means it's a more interpretable process. You can see what it's learning and break down the learning objective into smaller problems, kind of like what the motivation behind progressive growing of GANs was, where we started with a lower resolution version of the problem that we were trying to solve, learned how to solve that, and then progressively got better in terms of resolution. But here we're doing that in terms of noise levels. The result of formulating the problem that way and using that idea is that we get images that are a lot more believable and a lot more realistic than GANs are capable of. These, I don't expect you to memorize these as always, but it helps to have some sort of mathematical context for what's going on. So there's two things going on. There's the forward process, which we talked about, where we start with a clean image, add Gaussian noise, and we break this process up over t time steps. For each time step, what we do is we calculate what the noisy version of the image at that time step would be, which is represented by this, and alpha is sort of contribution of noise element. So epsilon is what the noise actually would be, and you have a term that is talking about how much that contributes, and you have the image from the previous time step, which also has that contribution factor, the weight, and both of those are sort of complementary. And what that does is gradually it will get rid of all of the information from the original image since you're weighting it. The goal is to be able to start from pure noise and keep doing this denoising until you get a clean image. So at this point, we haven't talked about controlling the process. All we're doing is given an image containing just noise, you generate some image that looks realistic. Now, to know whether our images are good or not, or whether the model is doing what it should, we care about two things, as always, which is how we encode our outputs, how we formulate the problem, basically, and what objective we can sort of use as a surrogate to actually directly solving the problem, because we need something that's differentiable. And it looks like there's a lot going on over here. There's not much to it, really. The uppercase E term is expectation, and we have to talk in terms of likelihood and expectation since we're dealing with randomness. So expectation over the initial clean image, our noise function, and time step t. We include time step t since depending on which iteration in the diffusion process we're looking at, the amount of noise will also vary. So all of those things together inform our expectation. And then there's just this squared error term over here between our prediction of noise, which is this term over here. The model, remember that the model is predicting noise and then we subtract that rather than predicting the image itself. And since we're the ones who added noise, we know what noise we added to the image, which is also another just 2D matrix containing a bunch of random pixel values. So we can then calculate pixel-wise difference between that, sum the whole thing, and square that, and that gives us our error term. Putting all of that together, we now have a loss function that we can that is differentiable, and we can use to optimize how good our model is at guessing what noise was added to an image. The model is trained to predict noise that was added to the clean image. There's the mean squared error term, there's the expectation term, and then we are talking about why we include the time step t. Now we need to think about, well, just generating images from randomness without some sort of mechanism to control what you're generating isn't really useful to us, is it? So kind of obvious way once you get it, but it's clever when before you get it. You start with noise, denoise it, and for each time that you do that, if you also supply information on what class of object it should be, then you can use a classifier, kind of like a discriminator in a GAN, to say whether your generated image is close to that class or not. And using the gradients of that, we can, again, similar to a GAN, we can guide our optimization so that it gets to the target class. Does that make sense? We have a noisy image. We already have the ability to generate something from noise, but we want to guide it towards something. So we supply a class, like in this case, we want the output to go through a classifier that we know is good. And give out the label dog in this case. So if it doesn't do that, then since we have gradients for that, we'll also know what other classes it was kind of like and what direction we can sort of aim for that would maximize the desired class. So this is called classifier conditioned diffusion. This compared to GANs, we were just predicting a whole image in one forward pass, right? And then asking the discriminator, hey, this is a real image, or this is a dog, and the discriminator would be able to say, no, it's not a dog, or this is synthetic. And that adversarial game was played in like single steps. But since here what we're doing is adding noise iteratively, it needs a whole bunch of steps of adding noise and learning to denoise all of those intermediate levels. So it's slower. It's a slower process in comparison, especially once you add in the conditioning aspect, then that also involves another classifier in addition to just the network we use for our denoising step. Autoencoders, this will make sense in a few slides of why we jump back in time a little bit. Autoencoders have been around for a really, really long time. And this is a term that keeps coming up whenever we talk about neural network architectures. The core idea is that we start with some input, which is high dimensional and complex, and gradually extract features and distill it into a more compressed representation. So for instance, if you start out with a 3-channel 256 by 256 image, then by the time it gets encoded and makes its way to the bottleneck, it's about 12 times smaller than what the input was. And it's a rich, distilled representation that contains all the information necessary to get back the original image from it. And unlike something like run length encoding or zipping a file where it's deterministic and you're doing things based on, say, how many times a certain value repeats or stuff like that. This is based on composition of features like edges and corners and putting those things together. So it's very dependent on the distribution that it's exposed to. So within the full distribution, it will map out stuff in a way that maximizes the distance between features and minimizes distance between like similar features until we have a sort of vocabulary of features that are very distinct from each other and very effective at being composed to describe the input, the original distribution. So the latent space is a bunch of numbers. They're 8 by 8 by 256. So if you think of the left face of that cuboid, then that's an 8 by 8, and then you have a 256 length vector corresponding to each pixel in that face, and they're all real valued. So you would think that What if you took away the encoder part and only held on to the decoder? It's a logical assumption to make, right? Assuming you have a way to generate these latent space representations, knowing what, say, class or object they would correspond to, you could just directly plug that in to the decoder part and use that as input to generate that corresponding output, right? It's possible, but we're talking 8 by 8 by 256. That's kind of a lot to map out and have a saved vocabulary of, to sort of disentangle what all of the features within that are and what they all mean and how we could sort of generalize that to generate whatever we want. It's not trivial to do that. But what we are good at is generating tokens that are shorter, generating embeddings and predicting which embedding comes next, which token comes next in a sequence of tokens. So if we break down the problem of predicting contents in an image into predicting tokens of pixel values, then that becomes something that we can apply a transformer to. So there's this architecture called vector quantized GAN, which applies that idea. So there's a few components over here to take note of. There's a code book, which is the kind of like the vocabulary I've been alluding to. And there's a transformer that's able to model sequences of tokens that are in the code book. And we'll get to this part in a second, but just breaking it down. So there's, what does this block look like? I'll give you a hint. It was 2 slides ago, I think, or maybe the 1 slide before. An encoder, this would be a latent space, and then a decoder. Yeah, it's an autoencoder. So the difference between these, there's still representations of what's in the latent space, but there's this lossy sort of quantization step where you take, once you rearrange it into the sort of token structure that you eventually want to be predicting, we can think of patches of images in terms of latent space values. And we have a set of those latent space values that have been tokenized, and each patch can be described as a composition of those. Now, what the encoder will encode doesn't necessarily have to overlap perfectly with what's in the codebook, since these are all real values, right? So for instance, if your codebook has 1 token with the values 1, 42, 3, 3, your latent representation here might be something like 1.2, 41.9, 2.9, 3.1. And what we do is then find whatever the closest tokenized version of patches we have in our codebook, and just return that. So these are then quantized to the closest equivalent in the codebook. And then we use that quantized representation to train our decoder half, and we use that output with a discriminator that just classifies whether it's real or fake. So just going into the notation really quick, the encoder E takes in an image X and predicts, converts it to a latent representation once it goes through the encoder path, which we call Z. We have a codebook set Z, which is a set of embedding vectors. There's the quantized representation of this, which we find by finding the closest match in the codebook, which is a simple distance minimization problem. And since they're all vectors, you can just apply that in bulk. And yeah, from that, we get our reconstructed image, which the decoder G does. But we're used to using that for a generator, but just architecture-specific notation conventions. And there's also a discriminator, which classifies those. So there's the autoencoder style part. Then there's this, which is you're taking your latent space and remapping it to your codebook space by quantizing it and finding the nearest neighbor. And then comes the cool part, which is now that you have embeddings that are in your codebook, you can guess which one would come next. So this is 14233, which is the first row from over here. And it's just this thing flattened, basically. So if you got to this part, you have another token, which is in the codebook and has the values 94, 60, 22. Then for an image that was missing that token value, you'd be able to predict that, oh, well, 94, 60, 22 is usually followed by a 57. So that way you're able to complete a quantized token sequence and then throw that into a decoder, and you get your generated image. So the difference here, yeah.
So, what tokens or factors are those just?
They are vectors. So those would come from some sort of encoding process that generates these. And the transformer bit is useful when we're dealing with something that wasn't part of the original distribution that was used to generate the tokens that are in the codebook. Because we need a way to deal with unseen samples, right? So just find whatever is closest to what you have seen before, basically. This is in their same principle as why the GANs that we've seen have discriminators, because this is a GAN ultimately. And putting all of that together gives us images like those. It's pretty good, but not great. One of the complexities is that the latent space is, again, very rich and capable of representing very complex information. We take the idea of working in the latent space and apply that to diffusion. So earlier, we had to deal with image space, which is a lot bigger than latent space, as we saw in the autoencoder architecture. So there's a lot fewer numbers that we actually have to fiddle with to figure something out if we move from the image domain to the latent space domain. How that is integrated with diffusion models is you add noise, denoise, do all of that in the latent space directly rather than adding noise in the image space. So you start with whatever the encoding for random noise would be, and then denoise and decode that using VQ-GAN, but without doing quantization. And what putting all of that together would look like is something like this. So this is a latent diffusion model where we take our clean input, not clean, just take our input. We have our noise. We have our encoding step. Sorry, this looked like notation for noise. We have an encoder that generates an embedding and goes through the diffusion process to make a prediction, which can then be denoised using some denoising network. And then there's the previous time step, which we're also holding on to, that comes from state information. And putting those together, we're able to get another embedding, which can then be decoded back into pixel space. So the idea of adding noise to images directly is easy to visualize. It makes sense. You're just adding random small perturbations to all their pixel values. What does adding noise in the latent space really mean, or what does it do? Really quick, encoder, decoder, that there's a forward process which we forward reverse. We don't need to get into that necessarily. It's still same as the diffusion that we were talking about. It's just that the objectives of what we're doing at each step aren't as straightforward. We still have a denoising unit, and this uses cross attention for conditioning, which has to do with how we control what output we want. And we do that using either semantic maps, text, image representations, anything that can give you an embedding which will be in the same latent space as what it uses to generate images and encode images. Just for intuition, you can think of the autoencoder as kind of a translator that is doing dimensionality reduction and compressing it into a set of complex features, which is the latent space. Then you add conceptual noise, which is, so by sort of nudging your values in the latent space a little bit, you're adding noise to it, but what that corresponds to isn't necessarily Gaussian noise in image space, but rather you'll see other more structured artifacts if you were to try to decode that directly. And then what we want our denoising network to learn is which of that conceptual noise, now these are actual sort of features that those values represent. So which of those don't belong there? So if it's like an image of the Earth taken from the International Space Station, and there's like a burger where the moon should be or something like that, then you know that shouldn't be there. So it's kind of like that, trying to guess what feature representation doesn't belong with the others. And once that's done, we're able to decode that back into image space. So this part is kind of like a VQ-GAN, but we're not doing quantization here. There's a diffusion model that's doing noise addition and denoising in the latent space directly instead of image space. And there's conditioning to guide it to a target. Yeah. Some random so there's a few things we need here, right? We need just embeddings for good images in general, which is your set of all features that make up one scene. You also need an understanding of what features belong together usually. So what will go in is just regular images, the kind that you would want to generate eventually. Along with that, you can also supply maybe captions or I don't know, object bounding box coordinates, classes, other images that are similar to it, which also get encoded and embedded, and that information gets fused with this so that they're sort of nearby in whatever space this is encoding to. The idea behind diffusion is that there's a video that I've linked at the very end, which you can watch later, but it comes from autoregressors, which are an approach where if you remove one pixel from an image, then you can train a model to predict what that missing pixel is. Is that a fair statement to make? One missing pixel, you have all the context of every other pixel in that image, and you should be able to just predict one single value using all the other pixel values. When you try to do that, masking a really large part of the image and predicting that entire missing patch, that is kind of ambiguous because there's a lot more context that you're missing. So to solve that problem, long story short, the way they changed the approach was instead of deleting entire pixels, we sort of reduce some information, but still keep most of the information of that pixel. And we do that by changing the value a little bit, which is adding noise. So if you do that for a bunch of randomly sampled pixels, then that loss of information is distributed uniformly across the whole image, which means that you're losing less context. The difference is that there's two differences between deleting a bunch of pixels from one corner and adding noise to a bunch of random pixels all over. One of them is that not all of the information from one pixel is ever lost. And the second is that you're still maximizing how much context you're able to supply for one per third pixel. Are we comfortable with these two things? So extending that is the foundation of diffusion. And the goal is to eventually get rid of all information from the original image, which is how we end up at complete noise. But the predicting noise isn't really what we're trying to do, right? But what we want to do is just generate an image. And since we're dealing with neural networks, we always need some kind of an input. So that's why when we talked about just regular diffusion, we started with noise. Here, we're starting with an embedding. And to understand the space of valid embeddings, what we do is we gradually destroy the embedding until it's completely noise, and we learn every version of it in between. Okay, that takes care of this part. This part also, I think we're fairly okay with what's going on. We just have some additional information that is related to whatever image you're encoding, and then adding to your sort of global memory. And then we're doing the reverse process using denoising, which is getting back what the original embedding would have been like. And here it will generate something from that, which ideally should be the same as the input, I believe. Going through there, denoise it until you get back the original embedding, and that goes through a decoder, which then generates it. Yeah.
So if this network, if we want to generate new images, we have to give us image.
So if I take away this whole block or the encoder, right? I take away this, or I don't do the whole diffusion process or whatever, but with just this half, I have now a way to recover, to generate something from complete noise, right? Because the embedding at this point doesn't have any real information in it. So from here to here, you're able to generate something from noise. So the idea is, if you have a code book sort of thing like we did with VQGAN, where you're able to directly generate an embedding of the image that you want to see, then you can plug that in here, and that will give you a pixel space version of it.
One question, the diffusion, we were using like each denoising state, there was classification that was so that you can guide. In this case, it's directly generating an image. So there's no in between. Like
This conditioning, so if along with it will always start from random, but you can also add in whatever prompt you want here, which gets encoded to the same latent space, provided that you supplied things like that while training it. So if you have, how would you describe this? I don't know, what kind of dog is that? Is that a German Shepherd? German Shepherd dog sitting in front of a red bike on a car porch with a on a porch with a car in the background and a tree or something like that. You encode that whole sentence into the same latent space. If you're using something like what was the data set that had captions? Coco, yeah. That's cool. So yeah, if you have that information handy, you can also just plug that in while you're training this whole thing, and that means you get more sort of contextual information that also gets embedded into the same latent space. And that information can be fused with this. So you can add that to this embedding and then generate it, and that's your conditioning mechanism. Just high-level summary of all the differences, similarities. The core idea for autoencoders is just having a compressed representation from which you can reconstruct a close to real, close to original version of the input, and that is a lossy process since you're representing it in terms of features that are in it rather than actual components that are in the raw data. GANs, there's the adversarial process where you have a generator, discriminator, both of them try to outsmart each other. Diffusion, just regular diffusion, you're operating in image space and gradually denoising it and learning how to do the reverse at each step. Vector quantized GANs, we use the idea of latent spaces along with GANs and quantize our vector space and also maintain a code book and use the combination of all of those things to generate our images. And latent diffusion models, we directly deal with the embeddings rather than image space. So we're perturbing our feature vocabulary description of the original input and learning to denoise that. And the rest of it, I'll leave you guys to look into that. So CLIP, I touched on this last class. So one of the things sort of unique to CLIP when it came out was that it was contrastively retrained. What that means is contrastive training is when you have there's a couple of flavors of the loss function. Triplet loss is one of the most popular ones. And the name triplet suggests that there's 3 of something that we're optimizing for. One of them would be a positive sample, one of them would be a negative sample, and one is just a sample that the model is given. And the goal is to use that triplet to group together things that are similar to each other and form clusters of that in your latent space and maximize the distance between clusters that are different from each other. And that's done on both the image and text domains jointly to get this sort of shared image and text latent space. So then what you can do is take one of the embeddings corresponding to Pepper the Aussie pup and put it into a decoder that is also modeling the same latent space and generate that image using the generator. And DALI was the generator that they introduced for this along with it. So CLIP was how they were conditioning the generation for DALI. And we do that, they did it using a bunch of labels for classes, composing a more descriptive label using it, encoding that, and then using that more complex composition of class labels and how they're related to each other as a new label to encode these two. So what that does is, rather than just having individual classes, you also implicitly model a relationship of classes that are within the image. And this is this is a visualizer for diffusion, and it also talks about autoregressors and all of that. How we got to the idea of diffusion models. It's really cool. It's I could never wrap my head around what diffusion was before I watched that. So props to the guy for putting in the effort. I've tried animating some of these using 3Blue 1Brown's library, but it's really time intensive. So the channel is Algorithmic Simplicity. And yeah, so the initial part has to do with autoregressors, and I don't want that audio, but this is the part where you have a model that's able to do just regular classification, which is predicting where it should be on a curve, or which side of a curve it should be on. Then deleting pixels. Why doing that? Why trying to scale that idea by just deleting everything in an image is bad? The whole thing. So just I'd recommend watching that just to be able to visualize the whole process. Will really help cement it. And yeah, for all of these, the original link to the paper is usually on the slide at the bottom. So if nothing else, you can take that, throw it into something like ChatGPT and ask it to explain it, because then that makes it interactive. You can ask it whatever questions you want that you couldn't ask the author, and probably get a reasonable explanation and just keep poking it until you're satisfied. Okay, so time for a quiz. People at the back, I want you up front. If there's a seat up front that you can take where you'd have one seat on either side vacant, if there is a seat like that up front and someone's sitting behind, everyone gets 20% taken off. So what is this? The prisoner's dilemma, mutually assured destruction. I'm not sure what this falls under, but either way, if you don't want to put a ceiling on how many points you can get for the quiz, and also not screw over your classmates, then come up front. And I'll make it visible in a second. And if you've had issues with lockdown browser before, I have a bunch of printouts. So rather than trying to get it to work, just ask me for a printed version of the quiz and I'll give you one. I have 6, I think. Actually, I want to hold on to one of these because I made these prints really last minute, so I want to check them. Make visible, and let me also check the passwords really quick. How do I do that? Well, quiz show up for everyone? Cool. Okay. I think I go. There we go. Okay. Yeah. I got the cases right this time. All right, who needs prints? Oh, also, phones up on your desk, please, everyone. You need a print? Or- If you find the quiz challenging, odds are everyone else in the class also does. So just stick to what you know, and that'll ensure that scores are representative of how much everyone has understood. And when there's no outliers, that makes curving your grades up easier for me. So if you want to increase the likelihood of getting a better grade by curving upward, then just only do your own quiz. Is lockdown working for everyone today? Print? Yeah, I got you. Oh, sorry. Yeah, it's fine. Just use the print. Oh, I guess I didn't enable that. 20 minutes. So yeah, I guess you have until like 11:50, which is when class ends anyway. I don't think I can change that anymore. Yeah, I'm not gonna mess with it now. I don't know what's gonna happen if I try setting a timer now. I probably not gonna apply that retroactively. Okay. Uh, um, yeah, just say select all that apply. This should be 7 points. This one. But yeah, they have select all that apply, and those are 7 points. Yeah. 4 points is single and 3 points is true false. Fourteen. Okay, y'all get about 5 more minutes, and then there's a couple of things I want to ask everyone, so stick around for a few minutes. We're down to the last minute. 11:50. I want everyone hitting submit and shutting their computers. You don't have to wait until that hits 50 to do that either if you're done. Okay, that's it. That's time. I want computers lit down once everyone's done, just so I can tell at a glance. And hope you marked everything. give you one more minute. Okay, so well, what I wanted to talk about, everyone knows homework is out, I hope. Posted on Piazza about that. Let's see what so this, I didn't really realize until I got a question about the date for the final in Piazza. But okay, I think I gave you guys 10 days for this one. Let's see, what was it? Face filter. So this is due August 7th, which hang on. Okay, that should be better. Oh, don't want to see that. What am I doing? Easy learns. Okay, yeah, there we go. So that's August 7th. And I believe I put this out on Sunday. So 7th is like, it's definitely longer than a week. And we still have one more homework and one more quiz to go. So in the interest of getting all of that done by the 16th, which is the last day of the semester, and 15th, which is the last day that we'll actually meet. 15th is the date of the final. And I want to free up some time before that. So what I was thinking is I'll get rid of the requirement that the written part needs to be typeset for this homework and change the deadline. I'll move it back to the 4th, which still gives you a full 7 days. And I'll put out the next one on Sunday and give you another full 7 days and have that end on the 11th. And then quiz some point next week, either 6th or 8th, and final on 15th. Is that, yeah, Yeah. When is that? 9th? Okay. So the fourth homework, I'm gonna make it simple so you don't have to like figure out my code much. And does anyone have a better idea? You look like you have a suggestion. 3. That will, I feel like that will hurt you guys more than anything because it's reducing your like sample size. So if you got like a worse grade on 1 out of 3, that will hurt you a lot more than if you got a bad grade on 1 out of 4. I mean, if that's what everyone wants, I'm okay with it. uh, how many for keep the 4 homeworks hands? Okay, we prefer the bigger sample size, it looks like. All right. Is everyone okay with me getting rid of the LaTeX requirement and moving the date back to the 11th for this homework? Okay, okay. And for the next one, okay, you say uh, project report is due on the 9th, right? Would it help if I made the project submission on the 16th? Because that's the last. Who asked me the question on Piazza? Yeah, you. Would you be okay with that? Yeah. Plus, I feel like it will also give you some time. A lot of your projects are really ambitious, and I want you to see them through. I think you guys would like that feeling a lot of seeing it work. Okay, so this deadline for homework 3 gets moved to the 4th. Another one which will be released on the 4th and end on the 11th. Final on the 15th, and the project submission on 16th. I didn't want to put the project after the final just so that you get like a few days with where you don't have to think about anything else. But if everyone's okay with juggling final prep and project work, then okay, okay. Looks like we have a deal. All right. See you all on Thursday. 7 to 4, then 4 to 11, 3, homework 4. And project on 16th and final on 15th. Yeah, I just gotta wrap up here.